Hello everyone, welcome to week 10 lecture. Week 10, we were discussing something about Rouse model, and today we will discuss improved Rouse model, which is called Zim model. So before starting directly to Zim model, we will discuss some of the problem in the Rouse model, which already we have discussed in the previous week. But I want to repeat that question once more and try to uh, extend our idea from that. So this is question number 6, which we have already discussed in week 9 live session. But I want to repeat that question again, that in the Rouse model, relation between diffusivity, diffusivity and number of segments is given by which of these relation. So there are four options, and we proved that D Rouse. So I'm directly writing down the correct option. D Rouse is given by proportional to 1 by number of segments, 1 by n. How we got that? If you remember, we have calculated some quantity which is mean square displacement r of center of mass RCMT minus RCM0 whole square average, and we can write down all three component like this. So this will be averaged x 0 alpha comma t minus x 0 alpha comma 0 whole square of this and average. So we have already got some relation here, because this is both of them are alpha component. So basically this will be delta of alpha alpha 2 kt by xi 0 into time, and basically delta alpha alpha is 1 here. So the basically relation is given by this, and xi 0 is practically in xi, and if you use this relation, so there will be additional 3 here because of 3 component, and altogether we got the relation 6 kt by n xi into t. And if we compare this with our known relation, that gives out the relation that d is proportional to 1 by n. Even though we got this relation in case of Rouse model, but it appears that this is not the correct relation between diffusivity and the size of the polymer or number of the segments. So we need an improved model in some sense, and that's why that is the motivation for doing the improved model, which is called Zim model. So today we will discuss Zim model, and we'll try to get the correct relation between diffusivity and the size of the polymer. So this is, now I am discussing some questions from the week 10 lecture. So question number 1, which is true? Option A, Zim model is an approximation of Rouse model. Option B, Zim model is an extension of Rouse model. C. Zim model, I am writing in short, is alternate representation of RM Rouse model, writing in short again here, RM is Rouse model, and option D, ZM Zim model is opposite to the Rouse model. So basically, which of these is correct, and we'll try to see. So what we have done in Rouse model, suppose this is our one of the polymer segment, and suppose this is the nth bit of the polymer segment, and this is n plus 1 and n minus 1 bit, like this. Suppose this is n plus 1, this is n, this is n minus 1. So the energy of the nth particle associated with the nth particle was given by something like or the let's say force or energy. You can calculate it from this. Let's start with for energy first. So energy will be given by E of n is half k r of n plus 1 minus r n whole square plus half k r of n minus r of n minus 1 whole square. So this is the energy. This is essentially a bit spring model. So if you take a derivative of this, you will get basically force acting on a nth beat, which will be given by k of k into spring constant k Rn plus 1 Rn minus 1 minus 2 of Rn, and using the theory of differences, you can show that we have done this. This is the double derivative with respect to n of the R. R is the position of the nth beat. But we have considered in this case, the point to be remembered here, that the force on the nth bead is only due to the bead present on both sides of the nth bead, that is the n plus 1 bead and n minus 1 bead. So force on the nth bead is only due to n plus 1 and n minus 1. So this is an approximation that no other bead in the system is putting any kind of force on the polymer. So in the Zim model, we consider force due to each of the bead present in the polymer on each of the bead. So that's the extension from the Rouse model to the Zim model, where we consider force due to all the beads present in the polymer. So Zim model is not an approximation, but it is an extension of the Rouse model, of the concept or the concept of Rouse model, whatever we have discussed earlier. It is the extension on top of that. So again, Rouse model is also a bead spring polymer model. Zim model is essentially also that, but we are now considering the force due to all the beads present in the polymer system. Now, how to write down that equation is something like, if you remember that there is a relation between velocity and force, which is given by some matrix HNM Fm, this is Vn summed over all m. So this relation, where H is a tensor. So this HNM is called mobility matrix. Mobility matrix. So V is basically velocity. Velocity is relating. Velocity V vector is related to via some tensor, which is called mobility matrix or the Oshin tensor. Oseen tensor related to the force. Now force, so basically let us do one question here, that the effect of hydrodynamic interaction on polymer chains is captured by option A, Stokes tensor, option B, Zinn tensor, option C, Oseen tensor, what we have just discussed, Oseen tensor, option D, Einstein tensor. So here clearly the correct option should be the Oseen tensor, which is relating the velocity to force in case of hydrodynamic interaction is present in the system, right? Okay. Now in this case clearly the force will be due to, the force has clearly two parts. Force is given by force due to potential due to the spring or something, that force due to the potential, spring potential, and the random force. Random force is due to, there will be solute particles or solvent particles in the system. Solvent particle, basically polymer is the solute here. So solvent particle, those we have some non-zero temperature, and because of that there will be some thermal energy associated with the solvent particles, and that will give some thermal kicks on the polymer beads, and due to that there will be a random force. That at this we have discussed multiple times already. So there will be a random force. So, and if you remember in the Langevin equation, this random force was given by some term. So if you remember now Langevin equation, there it was some term like Fm, which we considered extra due to the thermal force or at the random force. It is random because there is no preferred direction of this force. From any possible direction, the solvent molecule can hit the polymer beads and give some force. So every direction is equally likely. That's why we consider this as a random force. Now force due to potential, force from potential will be essentially the del u by del Rm, and random force is essentially the Fm. So the correct relation now, V is n not equal to m h n m, the tensor, into two force del u by del R m minus plus F of m, random force on mth particle. Correct? So this is h n m. Okay. So using the similar idea as we have discussed in Langevin equation part also. So F is given by minus del u by del Rm vector, and this will in turn give you k of r vector m plus 1 plus k of into r minus vector minus 2r of m, and if you approximate this using difference theory, and this will give you del 2r del m2 basically. Now, if you apply the exactly same idea what we used in Rao's model, that we will take a solution xp possible solution and find out the form of the solution, and just like this in the Rao's mode, xp of t, which is 1 by n 0 to n dn integral over n cos, which is the our basis function basically, cos p by n by capital N r n comma t. So this xp will satisfy the equation, and then from this p we can get the pth mode of the pth mode. So in this case, instead of Rao's mode, we call pth mode as these modes we call Zim modes. And in this case, instead of tau p go like tau 1 by, it was p square. This was in the Rao's model, but in this case, if you do the calculation, you can follow the lecture. It will appear like p to the power 3 by 2. You can follow lecture for the detailed calculation, or Dewey and Edwards for more detailed calculation. But essentially, the pth relaxation, pth mode, the time associated, relaxation time associated with the pth mode is given by the first mode by p to the power 3 by 2. So if we now do a question here, question number 3, relaxation time for pth mode in the Zim model of an ideal chain is given by option A, tau p is tau 1 by p, option B, tau p is tau 1 by p to the power 1.5, option C, tau p is tau 1 by p to the power 3.4, or D, tau p is tau 1 by p cube. So as we have discussed, the correct option should be tau p goes like p to the power 3 by 2, basically 1.5. So this is one clear difference from the Rao's model in case of the Zim model, where we have explicitly considered the force due to all the particles present in the polymer system on the each of the particle. Instead of in the Rao's model, we have considered force due to the neighboring particle only. The spring, the particle attached by the spring with the mth particle, the force is due to that only. Apart from the force due to the random force due to the kinetic motion of the solvent particle. That motion, the thermal motion, the random force is present in both the modes. Okay. So then one more question, related question, question number 4. You have to find out which is not true. Option A, option A is Just a minute. So option A is motion of the polymer chain. Motion of the polymer chain affects flow field. Option B, flow field affects motion of polymer chain. Option C, polymer chain cease to move in zero flow field. Option D, effect of polymer chain on the flow field may be neglected in certain situations. So in this case, the wrong option should be this one, option C. The polymer chain is to move in zero flow field. So there will be always thermal motion associated to this, and there will be a motion. The movement ceasing is not a correct scenario. And again, from this relation, via the mobility matrix, velocity is connected to the force field, and that way this basically affects the. So that is the whole point for the extension in the Zim model. So all the particles affect the movements of all the particles in the polymer chain. So then in the next question, question number 4, question number 5. In the Zim model, relation between diffusivity and number of segments is. So in this case, the relation is correctly come out to be d Zim is given by 1 by n to the power nu, which is indeed the correct relation. How to see that this is the correct relation? So suppose diffusion constant is given by kVt by 6 pi eta r, but this r is basically Rg. Now from our earlier discussion that we have identified that Rg is goes like n to the power nu, and this nu is basically the exponent in the different case. So nu is equal to 0.6, it can be 0.5, or it can be 0.33. 0.6 is for SAW kind of polymer chain, this is random off kind of polymer chain, and this is globule, collapsed globule kind of polymer chain. And depending on the solvent nature, this can be also identified that this is basically good solvent. This RW is associated with theta solvent, and the globule is associated to poor or bad solvent. If you remember this relation, we have derived this earlier, that Rg goes like scaling law of Rg is something like this. So now, if d is proportional to 1 by Rg and Rg is proportional to n to the power nu, then clearly d is proportional to 1 by n to the power nu. So this is one justification from what correct relation we got from the SIM model, that indeed d should not be 1 by proportional to n, but it should be 1 by n to the power nu. So let us move to next question, question number 6. The elastic energy of rubber is option A 5 kBT by Re square by 2 Nb square, or option B 3 kBT by Re square by 2 Nb square, option C 5 kBT Re square by Nb square, option D 3 kBT Re square by Nb square. Now how to do this? We can use some of the older idea we have already discussed to solve these. Suppose in 3D, half k r square will be associated with the kinetic energy, and that will be 3 by 2 kBT. From these we can calculate what is the spring constant in this case, and this r square will be averaged, and that r square average is given by approximately Nb square. So 3 kBT by 2 will cancel, so 3 kBT by Nb square is the spring constant. So the spring energy associated with this will be half k into n distance square, which is 3 kBT Nb square into Re square. So this is the correct relation in this one. Option B. So there was one more related question, that using which theory we can get the elasticity of the rubber. So basically elasticity of the rubber is given by the Kuhn theory, so which is discussed in the last section of this week lecture. And if you remember now, that also there is one small question regarding this. It's marked as next question, question number 7. Rubber is a fill in the blanks type question. Cross-linked polymer, concentrated polymer, option C, semi-dilute polymer, option D, polymer melt. So essentially in this case, as you know, rubber is a cross-linked polymer because there are multiple chains which are cross-linked like this, and that forms the element rubber. So this is a cross-linked polymer. This is the fill in the blank type question. So rubber should be a cross-linked polymer. So then one more question, the next question, question number 8. The history of deformation can be described using Oseen tensor, deformation gradient tensor, option C, gyration tensor, option D, asphericity index. So as we have multiple times discussed that Oseen tensor is basically the tensor, the matrix which relates velocity to force. So as we have discussed this relation that V is given sum over H in M if M. So this matrix is the tensor, is the Oseen tensor. So it has nothing to do with history of deformation. So what can be the correct option here? So basically asperity index is given by how one material is not circular. So how much it is deforming from a spherical nature. If asperity index, so basically this asperity index measures if something is not spherical, if it is ellipsoid or some other structure, it is how much it is deviating from the spherical structure. This deformation gradient tensor is basically given by if something is some object is given some stress, shear stress like this, shear like this, that object is deformed like this. So this will be a shear produced here. So in that case, the deformation gradient tensor basically measures that E, which is given by, it has altogether nine component: EXX, EXY, EXZ, EYX, EYY, EYZ, EZX, EZY, EZZ. And what are these elements is basically delta x prime. So delta x prime is the change position of any material point. So del x, delta x prime, del y, del x prime, del z, del y prime, del x, del y prime del y and del y prime del z. Similarly, in the last one, del z prime del x, del z prime del y, del z prime del z. So basically this tensor is giving you the history of deformation, in which direction it is deformed, how much. So suppose in some scenario, if x prime is given by x plus gamma y, where this is the gamma and this is the x direction, this is y, this is z, in that case, and y prime is given by y, z prime, because the shear is applied along the x direction only, in that scenario deformation gradient tensor is, by calculating all these, so in the direction of y prime and z prime there is no change, because the shear is applied only along the x direction. There will be a change in the material point, any material point that is given by gamma y. So this is x. So the deformation gradient tensor will be, in that scenario, E is given by 1 gamma 0 0 1 0 0 0 1. So this is called the deformation gradient tensor, and from using this you can get the history of deformation. So basically in this case, as you can see, that this all diagonal element will be 1 from this relation, whereas this only this term will be not 0, which is surviving, and this term is given as gamma. So this is the deformation gradient tensor. So in this case, the right option must be the deformation gradient tensor. Okay, so we have discussed some problems from Rao's model and some extension of Rao's model and Jim model, and some idea of how to calculate the mobility matrix or Gaussian tensor, and in this module, and how can we extend this idea of uh, taking into account all the force generated by all the polymer molecule, basically the hydrogen interaction, taking into account how can we write down the whole equation of motion and how things change in that scenario. We have got two ideas, that the relaxation of the pth mode, pth Jim mode, is no longer proportional to 1 by p square, but it is proportional to 1 by p to the power 3 half. And whereas we in the Rao's model we got, as we have seen here in the first question, that from the calculation of Rao's model itself we got the relation diffusivity is proportional to 1 by n, which is not true in reality, and the real scenario where diffusivity is proportional to n to the power nu, that we can derive using the Jim model idea. Yes. Okay. Any doubt? Any doubt here? So I must add to this that this deformation gradient tensor you can also write in a compact form like this. So basically deformation gradient tensor in a compact form, deformation gradient tensor is given by del R alpha, del R 0 beta. So basically, if there are three values of alpha and beta, there will be total 9 component of this whole matrix. So that's what, if we expand this, alpha is equal to x, y, and z, and beta is equal to x, y, and z, there will be, so 0 represent the initial thing. So similarly, one more quantity can be defined in case of velocity, that is defined as k alpha beta and t, which is renamed as velocity gradient tensor, which is k alpha beta t del v alpha del r beta. So in case of so this is useful. So this deformation gradient tensor is mostly useful if the material is a solid, whereas this is more useful in case of a deformation of a this velocity gradient tensor is more useful deformation to study the deformation of Newtonian fluids. So in this case also you will get a matrix. So k alpha beta t is a matrix kind of thing, which is del v, similar to this, del v x, del x, del v x, del y, del v x, del z, like this. Here we got that x, y, z in the denominator, del x prime in the numerator. So here also similarly we can write down the 9 components of velocity gradient tensor. So the second row will be del v y del y, sorry, del v y del x, del v y del y, del v y del z, and this will be del v z del x, del v z del y, del v z del z. So this is called velocity gradient tensor. So this is useful in studying the deformation of the liquids, Newtonian fluids. And this, the other thing, the deformation gradient tensor is mostly useful for studying the deformation of the solids. So we'll extend the idea of this deformation and how to study that using relation and what is the viscoelastic nature of polymer in the coming lectures, more using this idea of deformation gradient tensor and velocity gradient tensor. Okay, if there are no more questions, is there any more question? If not, let's stop today's discussion here. We'll meet next week with the next module and some problems from there. Thank you. Good night.